could start. Today we are excited to have another seminar here. Today is the graduate student version. I think it's the first one of this semester and the last one again, because I don't know if we are going to have another one. And today we will have Raman and Brianna. Each of them will have about 15 to 20 minutes, okay, and she's on. And 15 minutes of question. If you prefer to have questions during the presentation after. After would be better, but I'll you guys. All right, so we will start with Raman presenting about localized geomagnetic storms for forecasting from sun to mud. So that's it.
Thank you, Joseph. Yeah, I don't think I need to say anything more about that. So we can go on. Yeah. All right. So I'm talking about magnetic perturbations. This specifically changes to the Earth's magnetic field caused by solar wind impulses. That's the primary driver anyway. And you have seen this diagram on the top right probably hundreds of times. And that is a good depiction of, the main processes that go on. But something that is a sort of secondary effect, but still vastly important, and contributes a lot to the complexity of trying to understand and forecast geomagnetic activity, is the second half of this GIF, where activity in the tail causes high energy particles and flux transport towards the Earth. And that is maybe less energetic overall than like a CME hitting the base side of the Earth, but it causes a lot of localized structure in the magnetosphere and the ionosphere system. This is a little hard to see beneath the chart, but this is Scandinavian Peninsula. And so these current systems in the electrojet are only a couple hundred kilometers at most in diameter. It's very small compared to the picture you normally see up top. So this is sort of a problem in a forecasting sense, because you don't want to predict what is going to happen in Helsinki and say that's going to happen everywhere in the region, because it won't. And it's also a scientific problem because the causes of that degree of fine structure aren't really known to maybe the best degree we could. So I'm going to expand on the forecasting issue here. Forecasting is really hard. The reason is because we start from the sun, which is 150 million kilometers away, and we look at its effects throughout the entire what I'm calling sun to mud chain. You have the sun, you have to model all of the complicated phenomena that go on in the solar atmosphere and external heliosphere. That includes the turbulent and chaotic solar wind. That includes the geospace environment. That includes the geophysical environment, that the interaction of all these phenomena with the conductive Earth. And then if you're looking at natural hazards, you want to know how those this entire product of processes interacts with the power grid or with directional drilling or fluid pipelines, which all suffer detriments from geomagnetically induced currents. So how did we actually manage to deal with that? Well, I mean, it's possible to do so with physics-based modeling, I think, but a very practical and convenient way to approach this is from a machine learning perspective. So I hope to convince you that machine learning will be of benefit in this scenario. First of all, the model you build, you don't need to know the physics beforehand, not strictly so. All you need to do is provide it enough input data to develop approximations of the physics during the training period where you're building the model. And then you don't really know what the model learns until it's done training. But then afterwards, there are techniques to go into this inside the stereotypical, neural network model and figure out, based on the connections that are formed within there, what physics did it learn? And is it something that verifies or contradicts your beliefs, or is it something completely new? And sometimes that is the case. And then importantly for forecasting, once you train a model, which does take a long time, afterwards you can run it almost instantaneously. You can, what they call inference or forecasting. You can say, okay, given this set of input parameters, what is going to happen? And that is very, very fast. So I'm going to talk about two different things. First, I'm going to talk about my own work, but first I'm going to talk about work I did over the summer with the FDLX project, which is a public-private partnership between Trillium Technologies, NASA, Google Cloud, NVIDIA Corporation, and that's it for this time around. I was on the multi-scale geoeffectiveness team, which was a small team of myself, Mike Haynes, and Sahithi Yarmili, who are both the researchers in this sort of research incubator program. And we have some faculty on the right, Vishal Vashi and Amos. They were serving in an advisory capacity here, but the techniques that we developed were, many of them were originally implemented by these two on the right. So we did two main things during this research sprint. The first thing is we developed an upstream solar wind forecaster. So I'll go into the details of this later, but what we do is we take solar remote sensing data this is from the SDO satellite. And that imagery allows us to regress the solar wind measurements. So we have 6 solar wind parameters that we try and predict. Okay, here's an image of the sun. Can you tell me in a few days when the solar wind from that sun reaches the Lagrange 1 point, what the density is going to be, what the speed is going to be, what the vector magnetic field is going to be, so on. And then we have a downstream model flying over here downstream. Given L1 data, what are the geomagnetic perturbations going to be? This is also regression, and we do this in kind of an interesting way, where in order to deal with the localized nature of the geomagnetic perturbations, we actually have we don't predict the values of the perturbations themselves, but rather a spherical harmonic representation of them, so that we have a series of spherical harmonics fit to ground truth data, and those allow you to get a global picture of what's going on. You'll see that in a second. So this pipeline is a bit complicated, but I'll try and break it down pretty simply. So the first component, which is the solar wind forecaster, we call sheath. This starts with the solar imagery. This is AIA and all 3 components of the HMI instrument, which is a magnetogram, or creates magnetograms, I should say. We do some dimensionality reduction on the data set by looking at the images we get from the sun in these 12 passbands from the AIA and HMI. We crop the images to the solar disk, then we crop it further to just a small area surrounding the a vertical slice surrounding the central meridian, just so we know that the model only considers the Earth-directed features of the sun. And then we do some masking. We identify all the places in that slice where there are coronal holes and where there are active regions in an automatic process. And then we can calculate the total area of the active regions, total area of the coronal holes, and the flux of each of the components of the AA wavelengths or the HMI magnetic field components through those areas. And that ends up with 13 features, which is a lot less information than a full image being passed into a model. It does work pretty well, though, which I will show you in the next slide. You feed this into a solar wind regressor, and I won't go into too much detail about the machine learning information, but I'll be happy to talk about that in questions. And this is an XG boost, gradient boosted true. we get some solar wind forecasts, so some time series of temperature and wind speed, et cetera, that we then have the option to put into the downstream model, or we can use real data to put into the downstream model to predict from L1 what the magnetic perturbations are going to be on the ground. We have a gated recurrent unit scheme that looks at the time history of how the solar wind varies to determine, because we all know the magnetosphere is a very inertial system. It looks at the time history to determine what the spherical harmonic coefficient should be in order to best fit the ground truth magnetometer data that exists. And then when you run inference, you will through this whole pipeline can, in theory, get from just solar imagery, just a reduced sample space of solar imagery to geomagnetic perturbations. And so here's some examples of what those look like. So on the left, it's the blue is the actual solar wind value for that feature, and the orange is the prediction from Sheath, the solar wind handler for that feature. And then on the right is what those information look like when they're propagated to the downstream model, and show you on the northern hemisphere of the Earth what the deflection of the magnetic field is going to look like. The dots being the actual values, and the smooth histogram sort of thing being the predicted values. And this is pretty good, I think. Especially based on the errors I've displayed here in the bottom. But there is a bit of a caveat, which is this model, due to the limitations of the training data set, was not trained on any flaring time, so it misses basically all coronal mass ejections. So this test set is on a co-rotating interaction region storm, which performs very well on that, but it is not the most interesting, most complicated geomagnetic storm or solar event that you could imagine. But I can talk more about that if you have questions. Now just look at the downstream model using real data, not from the sun. We can validate based on what the model forecasts for each location on the Earth, and then if we have a station at that location, we can compare the real value with predicted value. And there's a range of performance. Some of these stations have wildly different magnetic field values than what's actually predicted, and some are fairly close for this type of model.
Is there any geographical bias in which stations end up on which list?
Yeah, that's a good question. So I think there could be some preference towards high magnetic latitude having better performance, but it's not a strict correlation. So it's that's just my initial conclusion here. All right, now I'm going to talk about what I have been doing at UNH, not involving any of the FDL stuff, but quite in a similar vein here. So I, again, will answer questions about a somewhat complicated method, but I'll give a rough overview of this. This is a spherical elementary current systems method, which is sort of like an electrodynamics informed interpolation system. Unlike the spherical harmonics, which is just sort of geometric, it gives you a value everywhere on a globe. This will give you a value everywhere in a region, but sort of takes in Maxwell's equations into account. So hopefully that's a bit better. The way it works is you assume that all magnetic variations you observe at magnetometers are due to changes in this thin spherical shell around the Earth, which you have as the approximation of the ionosphere. And then you can parameterize what value, the functional value of that shell as a superposition of these vector current systems, which each are centered at different points on a grid, although it could be any distribution you like. And each of those has a scaling factor, I naught here, that determines their relative strength to each other. From there, you can calculate how strong each current system needs to be, that I naught factor, in order to reproduce the this dBHDT is the time derivative of the horizontal component of the magnetic field. That's how fast it's changing horizontally. that you actually measure at each station. And that's basically fitting this model to the ground truth data. And then once you have that fitted model, you can, in a functional form, you can pick a set of coordinates and get a geomagnetic perturbation value at that point. So that would look something like this, if you do it at a single point, and then you can like extrapolate that to an entire region and make heat maps like this. So this is one of the tests I've done with that. There's a little title mismatch here, but in this, I compared a model that forecasts the ground magnetic perturbation from solar wind data with this spherical elementary curve systems interpolation method over North America. And in one model, I just had to do that. And in another model, it uses both the solar wind and data from the DMSP satellite, which is in a very low orbit, together to try and forecast what the ground magnetic perturbations will be. The DMSP has some ion parameters and then magnetic field parameters. The top here is the model without it. The middle here is the model with that DMSP data, and the bottom here is what the actual magnitude is measured. There's a lot of cutting out here because the data doesn't always exist. To freeze frame it here, it looks like the difference between the two models in terms of performance is not conclusive, which one is better. This is the RMSE, the Roomy squared error difference between the two models in terms of how well they predict each station. However, the model with DMSP data included qualitatively has some smaller scale magnetic perturbation features, and is even quantitatively much different results than the other model, which means that even if it's not the best predictor, definitely the information about the magnetosphere ionosphere system is important. Well, they may not be getting it right, but it definitely matters to the prediction. So, just in summary, the multi-scale nature of this long sun to mud chain has some various challenges that I'm trying to address with machine learning methods. For FDL-X this year, this research sprint, we created the sheep and the dagger model, which each regress solar wind and ground magnetic perturbations respectively. And here at UNH, since and before that, I've been using spherical elementary curve systems to try and get a more electrodynamics informed interpolation, and zoom in on particular regions to study, how these current structures and magnetic perturbation structures behave and to characterize them better. And as you may have expected, but just to emphasize, magnetosphere-ionosphere processes are really important in geomagnetic storms. It is not just solar wind variation. The context of the local system and the history of the system matters quite a lot. Oh yeah, and here is the magnetosphere. So that's it. Thank you. And I will answer questions.
We apologize.
So what's next for sheep and dagger? What's the intended, are you gonna continue developing those, or
Yeah.
where are they being shipped off to start?
So the thing we were trying to achieve initially was to only model coronal mass ejections instead of everything but coronal mass ejections with an empirical model that's designed to do that with potential field source surface models. I would like to do that. It's the problem with this is the empirical models that are made to generate CME structures are really slow to run. If anyone knows of a better way, a faster way to do that, please let me know. But right now, I think we're looking to sort of make that predictor, even though it's pretty good right now, we can always improve it a little bit. We also want to make it more comprehensive. For Dagger, there's plenty of stuff. There's a million experiments we want to try, and I can talk to you about that later, but it's too many people to get into that. I think this sheet is more important. Yeah.
Okay, I don't know anything about machine learning, always cool to hear it from. Did I understand this right? You focus on that, region of the sun that's directed at the earth, right? Because that's what's gonna affect the earth's system. So what goes in, as a training? And then what comes out, I think you mentioned 6 variables, what are those 6, and what goes in exactly, and what
Yeah.
from there you can get 6?
So, so these are 6 variables. These are got cut off. Sorry, this is IMF, the X, the Y, the Z, measured at L1. And then solar wind speed, this is ion or proton density, this is proton temperature.
And they would come from,
And these are provided by Omni. So L1 monitors measure those quantities, but we forecast them and then check how well the forecast was done with this model.
red sheet.
Yeah.
But like what goes in sheet?
Yeah, so what goes in sheath is, go back to the end. Images almost exactly like this.
Really?
This is a specific wavelength of light. There are 9 that are measured by AIA, which is the instrument that does that on board the SDO spacecraft. And then there's a magnetometer that measures the 3 vector magnetic field components in the chromosphere.
Oh, really?
And then you do some cropping, so you just look at the disk, not like the corners.
Right.
So you do another crop where you're just looking at the central area, right? And so you can see this huge coronal hole that happened. This is the storm that was actually modeled in the graph I showed you is from this time. This coronal hole extends all the way from the pole past the equator. And so if you just look at the central meridian area here, you can say, okay, well, there's this big coronal hole area that's like pointing at us. There's going to be high-speed solar wind coming out of that. And ideally, the model learns that that means co-rotating interaction.
So 9 different wavelength filtered images and the magnetic field data in Corona. That's with that, you tell the computer figure it out and you get the good match like that.
Yes, it's
Crazy.
very interesting to me. That's based on a previous work by Vishal Chandran, who was one of the people who actually worked on this model as well. That just did solar wind speed forecasting. And it was okay, it was pretty good, but what he didn't realize at the time was that that kind of process actually predicts magnetic field in the IMF variable. Yes.
Related question. So how does the sheath model train, right? Because you're looking at multi-day ahead forecasts and you will get enormous differences in the propagation time.
Yes.
So how, like, you can't train with, like, you train with a fixed time window or?
No, we do not train a fixed time window. What is done is during training, there's those 6 solar wind parameters I showed you, one of which is solar wind speed. So you do a ballistic back propagation of the solar wind to the time input. So you know the distance of the sun, you know the solar wind speed. If you assume that's constant throughout the entire journey, which apart from right near the sun, it is pretty much constant. Then you can say, okay, how long did it take to get to me? And you look that far back and take the image that corresponds to that time.
All right, but isn't the solar wind speed one of the parameters you're trying to predict?
Yes, so
How do you get around that circular logic there?
back here. So what we do is we would look at this blue curve. And we go back in time with that back propagation, that thing. And then we say, okay, here is the image, here's a set of images that we give you, the model, and here's the solar wind speed, right? And so it has this time differential and that wind speed are kind of related, right? But then in this sample, we would say, okay, here is just the image. We're not telling you the model, we're not telling you anything about the solar wind speed. And so based on the associations that it made during that training process, in which the time difference and the speed are connected because we impose that condition, it should make that connection on this out of sample data set.
Does it deals with the travel time as well, right? Or it just predicts that thing, but you don't know, like, if that prediction is gonna be on L1 or before or after that, how do you guarantee that?
So there's no guarantee, it is an assumption that does not always hold.
Okay.
But if you were to have a constant solar wind velocity,
That's the.
then you would always have the timestamp line up with the solar wind parcel you actually got. So if you measure a certain piece of solar wind and it had a constant velocity, then the image you looked at would be the image that produced that solar wind. Yeah, okay. Yes.
Quick, out of sync parameter, this really good, everything matches like a champ, but which one, there are variables that tend to be better than the other one?
Yeah, so this is just on this sample, but you can see this is the mean absolute error that the magnetic fields are quite close to each other, they're quite close to the real answer. Whereas the particle measurements are a little further away, so that's the speed, density and temperature. That seems pretty consistent from other samples I've looked at. I don't for sure know why that is, but the theory says that, you know, the SDO imagery, especially being able to see where the coronal holes and active regions are, those are like highly correlated with the IMF magnetic field.
So let's think, I was thinking of that.
Is it believable?
No, I clapped it. Oh, my mom told me two things. Oh, when you're gonna high five someone, you mean it. When you're gonna clap, you mean it. Great, yes. She never said that. Came up with that.
Times like this, I wish I'd listened to what my mother said. Why? What did you say? I don't know. I must listen.
Right. Right.
Alright, so my name is Brianna Isola. I'm presenting system science tools for MHD simulation. This project was part of the Los Alamos Space Weather Summer School. So these are only the results after 8 weeks. So it's an unfinished project, but I think we have some good results. And my mentors for the summer were Gianluca Delzano, Joe Borowski, and Kareem Sarafia.
No.
Here we go. All right. So some background and motivation. So comparisons and validation of magnetosphere codes have typically focused on one aspect or region. We've seen this with GEM challenges. We've had the Magnetopause challenge, Bayside Kinetics challenge, etc. So as a community, we need a tool to be able to analyze all the codes and all their complexity. So one solution is to apply system science tools to both the real magnetosphere and also our simulations. And so when we think of the magnetosphere, we can consider it a complex system of systems. So we know that it's driven. So this could be like the time-varying solar wind that transfers mass into the system. It's interdependent and connected. We have distinct plasma populations as one example. It's turbulent and we have emergent phenomena. And can we consider the magnetosphere complex? So yes, we can. Components are not homogeneous and they have a multi-level structure and complicated interactions that aren't always linear. And that is a reference paper for AP for review. And so what is system science? Because I said that word a few times. So system science is a methodology that explores a complex system as a whole, including all its interrelated systems instead of focusing on a single system. And so here our system is the magnetosphere. And so our basis for this is Earth system science. And when we do Earth system science, there's two components that are to be considered. The first is to apply system thinking. So we have to account for all parts and connections and have diverse expertise to match. The second tool is to apply the science of systems. So what is that? So that includes systems analysis and system science tools, which is the purpose of this study. So standard system analysis can include numerical simulations, analog mathematical models, and correlation studies, and there'll be more on that later. And so to give a project overview, well, we know that we've defined the magnetosphere to be a complex system of systems, and it is qualified to use system science methods, and that we know we can use correlation analysis. And so we define our overall goal, which is to perform a multivariable canonical correlation analysis to analyze the behavior of the magnetosphere and compare it side by side both with actual data and simulation. So this proposes two objectives. One, we want to see if the global simulation behaves as a real system does. That's incredibly important for validating simulations, which leads us to our second objective, to propose a new validation methodology for the space physics community. And so the simulation that we used in this study is the grid agnostic MHD for extended research applications, or GAMERA. This is created by the Center for Geospace Storms. And most of this information isn't really important, but some notable features include that it has a high degree of optimization, OpenMP parallelism, and it's pretty easy to adapt to different geometries. So it's a very flexible simulation to use. And we can also get a bunch of variables, including the supermag indices, which are used in this study, as well as others like the cross-polar cap potential, hemispheric power, and ring current total energy density. And so our methodology, we'll be doing canonical correlation analysis. So this is more of a theoretical background, and for the sake of this talk, this will be more as a reference, but we can actually simplify it a little bit. So canonical correlation analysis basically takes two state vectors, here it's the solar wind and the magnetosphere, and seeks to find linear combinations of these vectors that have the maximum correlation with each other. So we have our driver, which is our solar wind data provided by Omni, and then of course we have our magnetospheric data provided by GAMERA. And the output of this basically is we get a canonical covariate pair, a latent variable that is a linear combination of the state vectors with maximized correlation. So to kind of summarize what CCA does is we have our driver, the solar wind, and we also have a response magnetospheric variables. Those are written into state vectors with applied weights. These state vectors are put into a covariance matrix where the weights are optimized such that the two state vectors have the maximum correlation with each other. So I know that's a bit of a detail, but hopefully it's easy to follow. And as the output, we get our first canonical covariate pair, and we'll get a result seen here where we have our first canonical covariate pair for the Earth or magnetospheric variables, and then the solar wind variables, and we're able to see if there is a linear relationship. As a bit of a background, I wanted to include just important metrics that are done in this study, just in case those are unfamiliar. So the main ones that I'll just focus on for this talk are Pearson's R, or the correlation coefficient. And we also have the prediction efficiency designated as PE, which is a measure of skill based on mean square error. So this is just more of a reference. And for the summer, we wanted to look at two storm events. We have a March 2008 storm, which is the left-hand side, as well as the 2013 storm. For the sake of time in this talk, we're only going to focus on 2008, a high-speed stream storm. And essentially what we did is we were able to get a bunch of variables, both from the magnetospheric side and the solar wind, and we minimized the data set to include the smallest number of variables with the highest correlation for the study. So our inputs wound up being the density, the Z component of the magnetic field, velocity, and three supermag indices, SMR, SML, and SMU. And so here are preliminary CCA results. So the 2008 storm is on the far left. We also looked at 2013 merge, which we won't discuss too much for this presentation. But on the top, we have our observed data. At the bottom, we have a simulated. The y-axis is the covariate pair for the magnetospheric variables, and the x-axis is the first canonical covariate pair for our solar wind variables. We have a correlation coefficient for both of these about 0.8, and visually you can see there is a linear relationship there. So this was a good promising first result for CCA. We also looked at the convergence, or did a convergence study, and our goal here was to determine how much data is needed to converge on coefficients of CCA. Basically, how much data do we need to make this method effective? And so we have the observed data graphs on the left and simulated data on the right, but both are representing the same thing. The left-hand plot shows the relative error for the solar wind variables in red and the magnetospheric variables in blue over a number of points. And the right-hand plots are the correlation coefficient and prediction efficiency per number of points. The shaded bars represent a plus or minus 1% error for the actual value. And we can see that the data converges on the order of tens. So really, we only need a small portion of the data to converge. So CCI is a really robust method in this sense. And we know we don't need a lot of data despite having a lot. This is just an example looking at the individual variables, but we can skip right through that. And then next we want to look at how well do these variables correlate with each other? Are the same variables being driven in both the simulation and the actual data? So this plot's a bit complicated, but I'll try and break it down. So we wanted to compare individual correlations between observed and simulated data. And we can see that we have the data side of the simulation for both solar wind and the magnetospheric variables. And by looking at the correlation coefficient, we can see that both in the solar wind and magnetospheric, and for both the data and the simulation, we found that velocity and SMR are the top drivers in both the simulated and observed data. So a bit of a tongue twister there, but that just shows that there is agreement between the simulation and the observation. Next, we quantified individual weights. So this is quite a heavy plot, but since we're only looking at the 2008 storm, I've highlighted it here. So we have the darker value as our actual data and the lighter as our simulated. And we can see even without looking at the actual numbers, it is pretty similar. So we do have an agreement. So with our goal to determine if the weights of the data match the weights of the simulation, they kind of do, which is a really great sign. One thing to note is that we did use an amplitude weight. Basically, we just normalized all the weights by dividing from the maximum such that our biggest driver would be 1. And that was just a way to compare the data. Another thing we did was filter the data set. And so we wanted to see if we can determine driver response behavior by filtering the data set by specific conditions. So we want to ask, do we find the same variables driving in both the observed and simulated data? And are there consistencies in different storms? So that latter half we won't cover, but we can look at ways we did filter the data set. So a few ways we could do that. One is parsing the data. So we could parse the data above or below a threshold, for example, fast or slow solar wind. We can take a quantity and calculate the rolling average of it over maybe a 1 or 3 hour period, or we could filter the data by some type of variable. So this could be KP index or solar wind type. So we experimented with a couple, not all worked, but here are 2 that did. So for the 2008 storm, we filtered by solar wind type. There can be about 4 solar wind types defined for this study. We have streamer belt, coronal hole, sector reversal, and ejecta. The 2008 storm did not have ejecta, but we found that for our CCA results, we found highest correlation in sector reversal region solar wind input. So we had about a 0.8 correlation between both. Whereas our worst in this case was the streamer belt, which had about a correlation coefficient of 0.6 respectively. So that was a good indication. We did try this with the 2013 storm and found consistencies that the sector reversal did perform best and the streamer belt performed worse, which was good to know. So this is just comparing the weights with the solar wind type. So we can see that there was the unfiltered data set generally does well, but when we do filter it, we get kind of mixed results. So I highlighted the coronal hole here, which sometimes does perform really well, especially for density. But when we look at the magnetospheric variables like SMR and SML, it doesn't perform as good, which is surprising because coronal hole also didn't really perform that well when we looked at our CCA results. So this is kind of a heavy graph, so please stop me if you need any clarification. But basically, this wasn't exactly conclusive, but we did have some agreement, which was good. Another example is that we filtered the data by IMF, basically a positive or negative BZ. And we can see overall there is actually pretty good agreement. We do kind of lose it on the SMU index where we find worsening agreement. And for both studies, for both parsing by solar wind and by looking at BZ, we found that overall the solar wind variables had better agreement than the magnetospheric. And finally, we introduced a lag. So we wanted to determine if we can improve correlations by introducing a physics-based lag driver between the responses and figure out why or why not it works. And for those unfamiliar, essentially we took our response for the magnetospheric variables and shifted it by some time lag. After we shifted it, we took that truncated data set and calculated and did a correlation analysis for the whole system with that time shift. So this was done at the very tail end of the summer, so we haven't really gone too far with it, but we did see that when we looked at the supermag indices, we did get improved correlation, although minimal. So we have the observed data on the left and the simulated data on the right. And we can see that for the lag that we introduced over a 60-hour period, we actually do get a higher correlation coefficient. Although it is very small, it goes to about 0.82 to 0.87, that's still an improvement. We're still looking into why that happens and why sometimes it doesn't happen, such as in the 2013 super. And so for future work, we've only used 2 storms this summer. We definitely need more data. We want to create a larger merged data set for analysis. So I'll be running more of the Gamera simulation this semester to hopefully get some of that. And also not all magnetospheric variables were tested. So we did look at the supermag indices and minimize them from those inputs, but we didn't look at all the magnetospheric indices that Gamera had to offer. So perhaps there could be a bigger driver in there that we just didn't test. We also want to explore different MHD simulations outside of Gamera, because of course we want this to be a validation method, not just for this simulation, but one for all. And we might also look at nonlinear methods, such as kernel CCA or deep CCA, which can account for nonlinear relationships, as CCA really only accounts for linear. So to summarize, again, the overall goal of this project was to perform canonical correlation analysis to see if simulated data behave the same way as observed data in the magnetosphere. And so we had our first objective to understand if the global simulation behaves as a real system does. Does it? Are the same variables driving the simulation? Yes, mostly. 2008 was our best storm. 2013 consistently underperformed just a little bit, but there was overall agreement between the weights on both sides. We did filter the data to get more clues of what's going on, but nothing is confirmed yet. And then for our second objective, we wanted to propose a new methodology method. So for example, it wasn't very much indicated in this talk, but the simulation consistently likes the SMU index over the actual observed data. So could this explain something that Gamera is doing that might actually show an inconsistency or an inaccuracy in the simulation, and how can we resolve that? So that's part of our second objective. And then that's it. I wanted to thank the summer school and my mentors. And are there any questions?
So regarding the Gamera data, could you elaborate a little on how you ingested the model data? Because I know there's a lot of data that goes into the model runs.
Yeah, so it was pre-prepared for me by Korean.
Gotcha.
So I'm just learning how to run the simulation now, but the data I received basically just gave me the outputs of the actual inputs that I was looking for. So I had nothing to do with the actual preparation of the data.
Yeah, as far as the spatial sort of aspect of that data, was it a particular location in the simulation that you were pulling those variables for the correlation, or?
Yeah, the global magnetosphere.
The entire, okay. You go.
Okay.
My question is exactly related. Where did you get the data for one simulation, like the specific region on that sphere?
Yeah, so we want to look at the whole system, so it's the whole system.
2 questions. Is it sunset or sunrise?
Sunset.
Sunset in New Mexico?
Yes.
Whoa.
Yes.
Okay. I wonder if the machine learning to tell what is sunset or Mexico. Anyways, the linear combination, there. Can we go to that slide where you have 2 arrows coming in and the matrix? And then,
Oh, the.
yeah, it's much earlier. I don't even know what I'm gonna ask for that. Well, because I think that's where like the idea comes in, right? Okay, and here Yeah, can you walk us through the flow chart, like one more time, what's happening?
Yeah, so this is a very simplified description, but should give you an idea of how this works. So basically you have your driver, here it's our solar wind variables, we get that from.
Actual data, yeah.
Yeah, actual data,
Right.
and then we get our simulated data, we also have actual data of the magnetospheric responses to compare. But in this case, we have a response, which is magnetospheric data from Gamera. You put them into a state vector where each variable within the vector has an applied weight. These state vectors are put into a covariance matrix, and then the weights are optimized such that when you get your output, the two state vectors have the maximum correlation of each other. Basically, it's going to indicate, is there a linear relationship between the variables in both data sets? Are they related to each other? Of course, correlation does not equal causation, but it is a good starting indicator.
And so the coefficients are based in the weight.
Yeah, so you can kind of consider, that state vector, you have like weights A1 through N, and then the variables, that's 1 through N. the
And
data.
so that's one of the things you guys are investigating in tuning.
Yeah, and like, for example, we started with maybe 9 variables in total between the solar wind and the magnetosphere. And so we had to consider which ones we want to start with, which ones maybe a group of 3 and 3 that had the highest potential correlation with the smallest amount of variables. So that's also something we're playing around with.
And did you get into any trade-offs of whether having additional variables significantly improved your fit?
Yeah, so we actually started with all the inputs given to us, and we had a higher correlation, but then when we actually looked at filtering the data set, like for solar wind type, it was doing much worse than when we just used like 3 and 3 for solar wind and magnetosphere. So we have a lot of playing around to do, which is kind of the fun of it, but we found a set of 3 and 3 that worked largely okay for the summer.
I have 2 questions.
Yeah.
First of all, I was like listening to the whole presentation, going like, what about nonlinear relationships? But then you answered it. But so my question is, like, obviously deep CCA is going to be a lot more complicated, but was there a reason that you thought like the linear relationships would be particularly apparent? Or was it just like, we might as well investigate that first?
Yeah, so actually, let's see.
Or linear or non-coupled?
Let's see if I can actually, there was a previous study done by Borowski and Denton in 2018. I actually do have a backup slide for that. Let me see if I can find that. And so we had a good idea that this would work. So it's a good base plate to start, because of course this was just like a 8-week seeded project. We didn't know what was going to become of it. So we had a good idea there was some linear relationship. Maybe it can't describe everything, and we'll move on to something that can count for nonlinear, but we based it off of the study.
Yeah. Like most of the variance is along that.
Yeah.
And my other thing, which I guess is both a comment and then a question, is the 0.05 the correlation coefficient improvement. I think is actually, you said it was not much, I think that's a lot.
Yeah.
For an improvement, but then like it looked like it hadn't come to a maximum. Do you think that if you continue to increase the lag, it'll either asymptote or maximize?
It does plateau and eventually it drops. So this was done at the very, very end. So we were considering maybe it has to do with the solar cycle or some other cycle that maybe introducing a time lag would account for. We have not found any conclusions. And actually really interesting result is that I do have more slides for this. We found that SMR actually decreased pretty early on, so the lag did not improve it, which is really interesting. And this was only with 3 and 3 inputs. When we looked at all of our inputs, everything improved. So we have a lot to look into with the time lag, but it's in its very infancy stage.
Could that be because the difference between region 1 and region 2 current systems, region 2 current systems would take longer to respond to driving? Is that it?
I mean, that's a great assumption, but we just haven't done too much work into that, so it could be.
Right. Well, obviously, if you let the lags go too long, then what you're basically producing is an average state of the magnetosphere.
Yeah. And so we're even considering too, maybe only lacking 1 variable for improvement. So this was really done in the last week, and then we kind of just were like, okay, we'll explore this more in the future.
Right, and how do you inform what variables to introduce lagging? You have some physics-based reason for why you expect lag to be more important for certain variables than others.
Yeah, in some sense, we actually don't know. The good part about starting with a set of 6 variables total is that we can kind of mess around with the combinations to figure it out. If we do include more variables, that's gonna be tricky. So a lot of it is really just playing around and seeing, okay, well, if we lag all of them or one, how is that gonna to change? So for these examples, only SMR was lagged. We do have an example where all of the data is lagged. And of course, as we expected, you can't lag all the data, it's just gonna make things worse, but, so yeah, it's more just playing around with it. And maybe perhaps if we can find a way to filter the data to find something meaningful, it can inform how we might, or what we might lag, if we choose to include this.
Thank you so much.
All right, I think next week we are going to have seminar. I think the next seminar is November 8th. Unless we find someone else who can do that. You wanna do that? But yeah, but so far, the next one is November 8th, right? Thank you again.